What is integration? Imagine you're trying to find the area beneath a curve. One way to approximate it is by drawing rectangles underneath the curve and summing their areas. The more rectangles you add, the more accurate your approximation becomes. Integration asks, what happens when we use infinitely many rectangles, each with an infinitesimally small width, and sum up their areas? In this approximation, the width of each rectangle is a tiny change in x, which we call delta x. The height of each rectangle is determined by the value of the function at that point. To find the area of each rectangle, you multiply its width by its height. Then, by summing these rectangles across the interval between 2 points, which we call A and B, we get an estimate of the total area. But if we let delta x become infinitesimally small, we use dx instead. At this point, the summation symbol changes to an integral sign, which is like a smooth version of the summation symbol. This is the concept of integration, but how do we actually integrate? Take a function, for example, where x is raised to the power of n. The most common way we integrate this type of function is by using something called the power rule. The process is simple. 1. Add 1 to the power of x. 2. Divide by the new power. 3. Don't forget to add a constant, which we'll call c. Now let's address why this works. It's important to know that the power rule for integration actually came before the power rule for differentiation. Integration was developed first, even though most students learn differentiation first. The key figure here is Leibniz, whose notation we mostly use today. But Newton and Cavalieri also worked on these ideas independently. To understand the power rule, let's look at a few examples. Start with a simple function, where x is raised to the power of 0. This means the function is just a constant, 1. The area under this flat line, from 0 to x, is simply x. This tells us that the integral of 1 is x. Next, consider the function where x is raised to the power of 1. The area under this curve forms a triangle, which has an area of 1/2 multiplied by x squared. So the integral of x is x squared divided by 2. At this point, you might notice a pattern. When x is raised to the power of 0, the result is x to the power of 1 divided by 1. When x is raised to the power of 1, the result is x to the power of 2 divided by 2. It wouldn't be unreasonable to predict that if x is raised to the power of 2, its integral will be x to the power of 3 divided by 3. And this turns out to be true. Cavalieri confirmed this pattern for integers, and later, mathematicians proved it holds for all real numbers, except when x is raised to the power of -1. That's a special case for another time. Now let's move on to an example. Say we have a polynomial to integrate. This might look more complicated because it has multiple terms, but actually it's quite simple. Each term of the polynomial represents a small block of area, and because integration is a linear operation, we can integrate each term separately. Once we integrate all terms, don't forget to add the constant c. But that brings us to an important question. Why do we always add c? This comes from the realization that integration is the opposite of differentiation. Since differentiation came before integration, the two were not initially connected, and then once both Isaac Newton and Leibniz found the power rule of differentiation. They both will have independently realized that the two had exactly opposite patterns. To understand the geometrically why the two are related, you can think of it like this. Integration reverses differentiation by accumulating tiny changes to recreate the function. Differentiation, which finds the slope of a curve, loses information. For example, if you differentiate the function x squared minus 3x plus 5, the result is 2x minus 3. Notice that the constant 5 disappears during differentiation. When we integrate 2x minus 3, we know the result will involve x squared minus 3x, but we have no way of knowing whether the original function had a constant like 5. To account for this uncertainty, we add a constant, which we call c. Finally, let's talk about why integration was developed. Integration grew out of a practical need to measure areas and volumes. Ancient civilizations, like the Egyptians, used early forms of integration to measure land after the Nile flooded and to calculate the volume of pyramids. These practical needs laid the foundation for integration, long before it was formally tied to differentiation by Newton and Leibniz. To summarize, this video introduced the concept of integration, what it is, why it works, and how to use it. In the next video, we'll explore more algebraic techniques and tackle harder examples.